So, in the previous lecture, we have looked at when we were developing the representation using wave functions as the basis for C3V point group. So, we saw that for C3V point group, when we took wave functions as basis, that is Px and Py, what we got is a 2 cross 2 matrix, right? So, here for all three of them, and that was a irreducible representation, right? So that means although we started with px as the basis, we ended up getting a representation which is a linear combination of px and py, right? So we started with px, but we ended up with some coefficients with px plus py, right? So this was what we were getting. For example, when we were doing C3 rotation, we got minus half px plus or minus root 3 by 2 into py. So that means eigenfunction can also have degenerate eigenvalues. So what does it mean? So let us say that if we have degenerate eigenfunctions, so let us look at this example in more details. Degenerate eigenfunctions. Okay. So suppose E is our energy of a particle or a system is k-fold degenerate. What does it mean when I say k-fold degenerate? I will tell. So that means that if my psi I can be expressed as a linear combination of psi 1, psi 2, of course with coefficients c1, c2, c3 psi 3 plus ck psi k, and if h psi 1 is equal to E psi 1, H psi 2 is equal to E psi 2, and so on. So then I can say that H psi I is equal to E psi I, right? So all of them will give you same energy, and then there, if let's say there are multiple eigenfunctions which give me same energy, then if I take a linear combination of those eigenfunctions, that would also give me the same eigenvalue, right? So this would be, so in this particular equation, I would say that my E is k-fold degenerate. Like in this case, we found that our representation is two-fold degenerate, where px and py were giving me same eigenvalues, right? So similarly, now we are considering a case of k-fold degenerate, right? Okay, so let us further look at this. Let's say if we have r psi I can express this as a linear combination. So this can be written as r j I and psi j, where j goes from 1 to k, right? Because my E is k-fold degenerate, so I can express my psi a into k linear combinations of different eigenfunctions. And R is any particular symmetry operation, right? So this is a symmetry operation. Okay. So now similarly for any other symmetry operation, I can again write. So for some other symmetry operation, let's call it as S. I can write S psi. Now let's call it as some other index psi L. This can be written as summation m goes from 1 to k So I'm just using different index just to keep it different from the previous one. Psi m, right? So now R is a symmetry operation which is acting on a linear combination of eigenfunctions which are degenerate, and then S is some other symmetry operation which is acting on same linear combination going from 1 to k, and these are the corresponding coefficients of linear combinations, right? Not the coefficients here, so these are the corresponding characters actually. Upon doing, when R is operated, whatever character you get corresponding to each eigenfunction, this is the corresponding character, right? Okay, so now we can say that since R and S are members of a group, there must exist, as per group definition, there must exist product of R and S equal to T, which should also follow the similar behavior, right? So that means effect of T on psi should also be similar. So let us try to write down T, let's call it as psi n is equal to summation T, and let's give it as a index O. O goes from 1 to k, and this would be psi O. Okay, so now if we have this, so because R and S are members of a group, there must exist Rs equal to T. So if we say that the effect of T on the linear combination of eigenfunctions should be this, then if we calculate the effect of R and S onto a given linear combination, the coefficients should match, or the characters should match. So let us say if we combine the effect of R and S, what do we get? Combining the effect of Rs on psi I, we get psi I is equal to, so let us first operate S and then we will operate R. So if we operate S, we will get summation j equal to 1 to k, and we will get small s ji, and we will get psi j, right? So same way, so what we have done is we have just operated s onto psi a. Now next we will operate R onto psi j, so that will give us, or I'll just write it here, that I can take the summation out, j equal to 1 to k and sji, and I will now bring R into picture, psi j, right? So that R can operate onto this. And what do I have now? So then now I can write summation j equal to 1 to k, and I have sji, and now I can write this as another summation. Let's call it as m equal to 1 to k, and this will be rmj and psi m. Okay, now if I take those summation out, I have got j equal to 1 to k summation. So there's nothing fancy about it. This is just whatever we have shown in C3V point group. We are just doing it for a general k-fold degenerate case. Now this will be sji, and this will be rmj, and this will be psi m, right? Now since we can say that Rs is equal to T, so we have chosen this, that if Rs are members of a group, Rs must be equal to T. there must have a T as a member of the group, which should be equal to product of the two group elements. So that would define that this particular part over here should be equal to this part over here, right? So let us equate these two. What do we get? So we get, and we see that one of the summations is not required because we'll see. So we'll say summation over j equal to 1 to k. So I will write rmj and sji, and this should be equal to only this part t, and the index we can, of course, we can take this as mi. So do not get confused about the index. So indices, I'm just choosing that one. It's showing that all the linear combinations should go from 1 to k for different values. So indices don't have really any meaning over here in terms that what they are representing, that they're representing it's a k-fold degenerate case. Okay, so now if we look at this particular case, what do we have? What can we say about this? So TMI, what do we think? What is TMI? So TMI is nothing but it's a form of a matrix, or this expression is for the elements of a matrix T, which is the product of R and S, right? So if I want to write a general matrix element T, which is the product of the matrix R and matrix S, then I would get this expression, right? Thus, we can say that the matrices R, S, and T together they form a matrix representation of the group when the bases are a set of k-fold degenerate eigenfunctions of H Hamiltonian with a particular eigenvalue. So thus that will be a k-dimensional representation. This will be a k-dimensional representation, and it would also be a irreducible representation. We have seen again that in the case of C3b point group, that when we started with Px, we got a two-fold degenerate representation, which was an irreducible representation, and we can always test it with GOT, right? So that should be clear now. So what we have shown, so we started with an example of two-fold degenerate case, and we have shown that the same thing can happen for k-fold degenerate representation. So whenever your eigenfunctions give a k-fold degenerate eigenvalue, the IR representation that you will get using those wave functions or eigenfunctions as the basis set, that will be k-dimensional representation, and it will be a irreducible representation. So this covers the wave functions as the basis set subtopic of group theory and quantum mechanics. Next topic in this quantum mechanics is the direct product. We will see what the direct product is. Well, we would have all seen what is the direct product of matrices. It is very similar here, exactly same actually. So we'll see what is the direct product, and we'll see what is the application of this in group theory. Okay, so let's start with understanding what the direct product is. So suppose that R is a symmetry operation of a molecule, and there are two sets of eigenfunctions that form bases of the group. So let us write down one set as x1, x2, going all the way to x, let's say m. And the second set is, let's say y1, y2, and this one is going all the way to n. Okay. So now if we want to write in the shorthand notations, we can write it as r xi can be written as summation. The character obtained can be written as small x ji and x j, where j goes from 1 to m, right? So this was up to m. And similarly here we can write r operating on y, let's call it as k. This can be now written as summation small y lk, where L goes from 1 to n, and I have YL, right? So now how do we write the direct product of this? The direct product of the two basis sets is given by, so direct product we can write it as, let us say direct product as, so what you have to do is basically multiply each element of the basis set with the other each element. So that is x1 y1 comma x1 y2 x1 y3 going all the way to x1 yn. Similarly we have x2 y1 x2 y2 going all the way to x2 yn. Again similarly we have xm ym. So each element of the basis set is multiplied with each element of the other basis set. That gives you the direct product of the two basis sets, right? So now what we will show here is functions, maybe call them as perhaps eigenfunctions, in the direct product also form a basis for the representation. So what do I mean? So what I'm saying is that if the set of representation, that is, or set of eigenfunctions x1 x2 x3 form a basis, and y1 y2 y3 etc. form a basis, then their direct product will also form the basis of the representation. What is the use of that we will see, but let us first see that this is the case. So let's try to do this mathematically. So xi, a general product here, can be written as yk, and now if we apply r onto this, what do we get? We'll get two summations and we will get two characters over here, right? R will be applied on x as well as onto y. So we can say that this is ji and xj. So that means there will be summation of j equal to 1 to m, and then we will have y lk y l. So this summation will be going from l 1 to n, right? Now I can combine these two numbers and write summation j goes from 1 to m summation L goes from 1 to n x ji y lk xj and yl. Now we can substitute this. These two are numbers, so we can make a product and substitute this. So substitute xji ylk with z, and we'll combine the two indices jl and ik. I can always do that because these are numbers, right? Okay, so this means that I can write r xi yk as double summation z jl ik xj yl, right? This is summation over j, this is summation over l. Okay, but what do we have now? This is a general expression, this is a standard expression relating symmetry operation and eigenfunction, right? So we are applying, so as if we are taking this as a eigenfunction, we are getting one value as a character, right? So when we apply symmetry operation onto a product of eigenfunctions, we are getting the same product back along with the with some character. So this is a standard expression. So now that means if x forms the basis separately and xi, a linear combination of x forms the basis separately and linear combination of y forms the basis separately, what we have shown here is that product of xy will also be of the same form, and thus this will also form basis for the symmetry operations or for the particular representation given any symmetry operation. Okay, so one more point over here to discuss. Now we can say from this we will see that we can deduce that the character of the representation of a direct product. So now from direct product we get a separate representation, right? And that representation has some character, so we are talking about the character of that representation. So character of the representation of a direct product are equal to the products of the characters of the representation based on individual set of functions. So that means what I intend to say here is that let's say we have a general group E, A, B, and so on, and xi, that is x1, x2, x3, all of them are forming a basis set in general, right? And then their characters are, let's say, x1, x2, x3, and so on. Similarly, yi is also forming a basis that will give you a IR representation as tau yi. So this will give you y1, y2, y3, and so on. So if x and y are forming the basis separately, the direct product of that, let's call it as j, xi, yj will also form the basis, and their characters will be given by x1, y1, x2, y2, x3, y3, and so on, right? So this can be seen from here. So let's say we want character of z, let's say if x and y are individual sets of functions that form the basis, then the direct product is called by z. Okay, so we can call it as z. So xz under any symmetry operation, which is this one, let's say any symmetry operation e, a, b, c, and so on, is given by summation over small z, that is jl, jl, and now this can be written as summation. So I'm just using this equality, I'm expanding this, so this can be written as summation j, summation l, and I can say that this can be x jj and y ll, right? Now, and then I can separate this out as summation over j x jj, summation over l y ll, and now this can be written as character of x under that I r and character of y under that r, right? So the product of the two characters will give you the product of the character under the representation, which is formed by the direct product of the set of functions, right? So I hope this is clear. We will take examples of this and we will solve those examples in next class. Meanwhile, you can practice through the maths and then look at the indices carefully, that if you got this thing correctly. All right. I think that's all. We'll discuss examples in next class.